All right, well, it's a couple minutes after the hour, so I think we're going to go ahead and get started. Again, welcome to everyone to this morning's workshop put on by the Network for Innovative Methods in Longitudinal Aging Studies, or NIMLAS. Really happy to have everyone here for today's workshop. I just want to start with a couple of logistical items. You're welcome to keep your camera on. You're welcome to ask questions during the workshop at any point. You can submit those questions by chat, or you're welcome to just unmute yourself and ask the questions directly to our presenter today, who I'll introduce in a second. But either way, don't hesitate to chime in if you have any questions over the next 3 hours. We are expecting to go till about 1 o'clock, and Dan has scheduled a couple breaks in there just to give everybody a chance to get up and move around. So hopefully that schedule will work well for everyone. Remember that these workshops are recorded, so the recordings will be eventually posted on the NIMLAS website. I'm going to put the NIMLAS website in the chat here for everyone so that you can read more about upcoming activities and other events that the network has coming up. So we'll be in touch with each of the individual working groups with more information coming forward. You should have received emails this week and last week actually about the upcoming working group meetings that we'll be having in October and November. So please remember to save those dates on your calendars, and we'll look forward to making more progress with what each of those working groups are working on moving forward here. So this workshop has been in the works for a while. We've only really had one workshop on kind of methods for using weights when analyzing longitudinal data, especially with the kinds of populations that NIMLAS is interested in. So we were very happy that Dan accepted and was willing to put on this kind of workshop. Dan has provided a link to the NIMLAS website that shows where you can find all the materials. They're going to be publicly posted for a while. We have to work through some things related to the materials to keep them up in perpetuity, but they'll be up there for about a 1-week period. So please take advantage while you can. The R code and the R examples are going to be up there indefinitely. You just have to do some things related to the slides. But make sure to download those materials during this 1-week period while you can so that you have everything in your possession. And you're welcome to follow along as Dan is going through these examples today. So we want this to be pretty practice heavy in terms of how to work with these weights and then how to use them ultimately when analyzing longitudinal data. So thanks again to everyone for being here. At this point, I would like to introduce our distinguished presenter today. So Dan Liao is a senior research statistician and program manager in RTI's Division of Statistical and Data Sciences. She's been engaged in innovative survey research and data science for more than 15 years. She's worked on multiple aspects of data processing and analysis for large, multi-stage surveys of healthcare, including cross-sectional and longitudinal sampling design, survey weighting, data editing and imputation, statistical disclosure control, and the analysis of survey data. She was the statistical lead on mental health surveillance study under the National Survey on Drug Use and Health, and the sampling and weighting statistician on the 5th wave of the National Longitudinal Study of Adolescent to Adult Health, or ADHealth. Currently, she's the sampling lead on the Mental and Substance Use Disorders Prevalence Study. She also leads multiple statistical tasks under the NCSX NIBRS estimation project to address challenging issues in data quality for administrative data on crime in the United States. Her statistical training in survey design and analysis is complemented with training on data collection techniques, issues related to data collection mode bias, non-response bias, experimental design, and questionnaire design. As a program manager, she oversees a team of statisticians on technical issues, scientific stature, and other areas of growth. Dr. Liao has published research on regression diagnostics for complex survey data, calibration weighting for unit non-response, combining data from multiple sources, data quality improvement, Bayesian mixture modeling, and predictive modeling. She's also a very active member and educator in the survey statistics community. She teaches graduate level courses on applied regression at Columbia University's Mailman School of Public Health. Her extensive professional service includes positions such as the Associate Editor for the Journal of Survey Statistics and Methodology, the Methodology Section Chair for the Washington Statistical Society, and the Publication Officer-elect for the Survey Research Methods section of the American Statistical Association. So based on all that, again, it's really a treat that Dan has agreed to put on this workshop for us. We're very much looking forward to it. And at this point, Dan, I will turn the floor over to you.
All right. Thank you so much, Brady. I'm going to share my slides as what Brady said. We're going to take 2 break. So I'm thinking like maybe 10 minutes break at like at 11 a.m. and then 12 a.m. to just give everybody a break, for coffee and water. Feel free to add your questions to the chat. I will try to talk slowly so you have time to think. I also created 3 R practices. The first 2 are simpler. The third one is going to be quite long, and actually we're going to use ad health survey data to do some of the practices in order to apply the weights for making different estimations. So I will leave that to the third hour. So let's start. Okay, so hope you can see my slides. Okay, so today's session, actually, we're going to cover 2 different things here. One is how to construct the weights, another is how should I apply the weights. I think those 2 questions are tied together. Sometimes it's really hard for researchers to really understand, which weights I need to use unless you understand how we actually created those weights. So I think that makes sense to put them up together to discuss about the weighting topics for longitudinal study. Okay, so basically in my workshop, I'm going to have 4 different sections. First is to understand why should we use survey weights for longitudinal studies. And then we are going to talk about how to construct the weights for longitudinal studies. The third one, actually, this is something that, on non-researchers in the longitudinal study, it's very easy for them to ignore that actually when we are creating the weights for later waves in longitudinal study, we can leverage information we collected from the prior waves, right? So how we can use those information to construct the weights for the later waves. So I'm going to cover that. And at last, I'm going to talk about how we can apply the longitudinal weights for estimation. So for longitudinal weight surveys, I think all of you are experts in this area, or at least are doing some research in this area. Basically, this is like also known as panel studies. It collects data from individuals over multiple time points. So this particular approach to do longitudinal studies really enables us to model developmental trajectories and understand the change across the lifespan. And also for each individual waves, people can do cross-sectional analysis and can just understand at the current time point what the prevalence rates of different kinds of things looks like. So it offers both dimensions for researchers. So survey weights are values assigned to each observations. I think the main purpose for survey weights is to ensure that your sample can represent the target population. Because for statistics, right, when we are making the inference, our focus is really on the target population, although we can only collect data from a sample. That's why the survey weights can really helping us to bridge that gap between this is my sample data, this is my population data. If their distributions are different, how I can align my sample data better with the population data. So that's the purpose for survey weights. And in longitudinal context, actually, as what I will demonstrate later, producing and applying those weights is more complex than the cross-sectional weights. So for example, there are inherent temporal dimensions and then dynamic populations. So what does that mean here? For dynamic population, for example, if you are defining your population, for example, as adolescents born in 2010 and 2016, and then in the US population. And when you are like following with these cohorts for 30, 50 years, some of them will decease, right? So your population shrinks down because of that fact. And some of them may move abroad to other countries. So are they still qualified for your target, eligible for your target population? So that's what we are talking about, the dynamic populations. And the temporal dimensions could be like, some people join the studies and left and then come back. And sometimes we even have this refreshment sample. So we will add new samples into the panel later at the waves. So there are a lot of complications going on there. And so weights are fundamental for making valid population inference from the sample data. Again, this is to think about how I should accurately let my sample data to reflect your research population, your target population. So I would use two examples today to sometimes to talk about different issues. So one is I'm working on both. I'm not working on NLSY 97, but I'm actually leading statistical efforts for the new NLSY 27, which is a brand new cohort. I worked on health for maybe 10 years. So this is a national longitudinal study of adolescent to adult health. This is a major US research project designed to follow a very large nationally representative sample of adolescents from their teenagers into adulthood. So actually this study began in 1994 to 95 with a nationally representative sample of adolescents in grades 7 to 12. So the sample size is over 20,000 at that time. So it's very interesting because my age is also, within that range. So it's very interesting to see like data collected from these cohorts, and I can sometimes relate them to myself as well. So actually we've just finished the data collection for wave 6. So participants have been re-interviewed multiple times since 1994, 1995 for 6 waves now. So they are entering to their midlife. And we are also going to continue this longitudinal study and studying on how this cohort is aging. So this is a very, very rich data set. So I'm going to use AdHealth a lot, given its history in this talk. Another one I think complements with AdHealth is this National Longitudinal Survey of Youth, 1997 cohorts. So this is one of the flagship US longitudinal studies run by the Bureau of Labor Statistics. So the sample size is about 8,984 youth aged 12 to 16 as of December 31st, 1996. So actually, these respondents have been re-interviewed annually through 2011 and then biannually since then. So this is a very long history and longitudinal studies as well. And the differences between, one of the big differences between the two studies is AdHealth, they started selecting the adolescents from their schools back then. But NLSY actually started to selecting households in the United States. And then they go to households to find whether they have eligible youth in the household and then do interviews with them. So the setup is a little bit different. Just to give you some, picture about like how this AdHealth study looks like, because this is a very typical longitudinal study. And when we are kind of looking at a 30 years longitudinal study, a lot of things can happen. So one thing that happened is actually at wave 5, so around like 2015, 2016, we actually considered to convert the in-person data collection for this longitudinal study into a mixed mode study to modernize it, and also to save to be more cost efficient. So the mixed mode means that we offer web mail surveys to these cohorts, but we also do in-person data collection later for some of the non-respondents and for a control sample group in order for us to understand the mode effects. And the response rate for this longitudinal study, I think it's pretty good. So it's about like 79% for wave 1, and then about 89% at wave 2, 77% at wave 3, 80% at wave 4, 72% at wave 5, and currently we're doing wave 6, wrapping up the wave 6 data products. So you can see this is a very high quality longitudinal study in order to do panel maintenance, and also to try to follow up with those cohort members every few years. So why should we use survey weights for longitudinal studies? So the first thing is that we wanted to ensure representativeness, because the weights can ensure the sample remains representative of the population of interest throughout the study, even when we get panel attrition and the population changes. So one key component in constructing survey weights is that we need to consider the sample design. And usually, because a lot of the longitudinal studies are very big investment in terms of data collection, and they are also very, very valuable. So researchers at the beginning will always consider a lot of different factors in designing longitudinal studies. So the weights should also consider how we can reflect, for example, stratifications and the clustering, and how that, the unequal selection probabilities can be reflected in the survey weights. Another thing is that some participants may drop out over time or fail to answer certain questions. So that can introduce biases in how could we adjust for the non-response and attritions. And another factor, as what I'm saying, is population dynamics. So the target population itself can change, and this requires some dynamic weight adjustments. And sometimes when people are studying certain causal inference, they could use specialized weighting methods, for example, like the inverse probability of treatment weighting to address time-dependent confounding effects. So I think some of the other longitudinal studies have used similar methods in order to address confounding effects due to the time. And without the proper weighting, conclusions drawn from the sample can be quite biased and inaccurate. So that's why it's crucial for us to apply weights in some of their estimations. So the most important part for weights is to ensure the sample to be representative of the population, and the representativeness is vital to draw valid population inference, especially regarding to the developmental trajectories. So unadjusted data could misrepresent these trends. For example, in a lot of studies, they could try to oversample specific demographic groups. And if we're not accounting for those type of designs, then the sample could be skewed to really reflect the population average. So one thing, for example, in ad health, initially, because they are interested to study these particular groups of Black youth whose parents have high levels of educations. So they oversampled them to ensure sufficient power to study these outcomes. And if you are not adjusting your weights, for example, especially when you are studying Black youth, then your results could be quite skewed. Because actually, if you look at the population distribution, Black youths, their parents having high levels of education are relatively low, especially during 1990s. So you can make quite skewed, biased, estimation if we are not accounting for this fact. Another thing like NLSY, they actually purposefully oversampled Black and Hispanic youth also back in 1997. This is also because they want to ensure enough sample size to do analysis within those race ethnicity groups. So when we are making estimations for the entire population, we needed to use ways to adjust the sample back to align with the population distribution.
Dan, we had a question come in the chat on slide 8 here. So
Okay.
Alden says, if my estimand is a rate of change or an effect of a covariate on a rate of change, how much might sampling weights change my estimates of that rate of change? So with regard to what you're saying right now, so not just focusing on the descriptive, but like an actual rate of change, like how might weights impact those estimates?
Yeah, so your rate of change is also, we can consider that as it's like a difference estimate, right? It's the difference divided by the prior rate wave estimate. So it's a difference. If you think about a difference, it's just a mean value, right, across the entire population. So if you are using your sample to estimate the mean of a difference, if you just think about that, you still need to use the weights to adjust for the sample differences. So for example, in your sample, you have equal sample size for white, Black, Hispanic, and other race. Then your mean, without adding the weights, the mean of the difference will be based on a sample that with the equal distribution of the race ethnicities. But if your population has a very different distribution, then you are making a biased estimate. So that's why you still can apply the weights. And actually,
thank you.
Yeah.
Sorry, thank you. That's really helpful. I might be misunderstanding it, but let's say that I were to be using like a random effects model, and so my rate of change isn't so much a mean difference between two time points. It's kind of like a random effect. There's a random effect on rate of change. Is what you just said, does that still apply?
Yes,
Okay,
that still
thank you.
applies. Yeah. Yeah, because your random effects will then reflect that unweighted sample, which has a very different distribution than the population. So when talking about addressing complex sample designs, this is for a lot of longitudinal studies. They frequently employ complex sampling designs, especially for large-scale surveys. They have a lot of different stakeholders. So they have a lot of different interesting questions. So some of them are interested in particular groups. So they wanted to oversample those groups, right? And sometimes because of the data collection constraints, we can't go to every schools to select all the students or, do a simple random sampling that way. So maybe there will be some clustering. So their sample designs could feature like stratification, clustering, and unequal probabilities of selection. For example, for NLSY, it actually, when they designed it back in 1990s, they have a cross-sectional equal probability multi-stage cluster sample with a supplemental sample that oversampled Hispanic and non-Hispanic Black youth. So the equal probability multi-stage class sample, what that means is they actually did an area sampling, because this is a household survey. So they need to select the areas proportional to the population size. And then within each, so that means areas with more populations get a larger chance to be selected. And then within each area, they selected the same number of sample sizes, given the PPS proportional to the size sampling schemes. They will, like each household will have approximately equal probability to be selected. So as you can see, this is a multi-stage sample, so we need to consider like the stratification and clustering at all the different stages. And also they added a supplement sample to oversample like areas with more Hispanics and non-Hispanic Black to increase their sample size in those groups. So you can see that weights needed to actually account for all of that. And for ad health, initially they used a stratified cluster sampling design as well. So they also oversampled the particular groups. So we needed to account for those as well. So that's why this is what we call the design weights. So the design weights are used to compensate for all these initial unequal selection probabilities. And without accounting, then you will get incorrect statistical inference. The next important part for us to consider is handling the attrition, because we know that, especially nowadays, it's very challenging to keep all the cohort members, to have them to complete their interview at each wave. So this is what we call the non-response, right? So so how we can adjust for non-response through the weights. The non-response rates, for example, for ad health wave 5 is about 71.8%. So they are like about 28% non-respondents. How can we, let the weight up the sample to represent them also from the, from this sample survey weights? For an LSY in round 20, the retention rate is about 74.7%. And so that is like, 6,713 out of the initial 8,984 respondents. And excluding those that are known to be deceased, the response rate is about 77%. So this population is kind of changing as well. So attrition can significantly reduce the effective sample size and lead to a non-representative sample to bias the inference. So even when we are using the design weights to weight up the data, it's not enough, because in this sample, we also have dropouts. So we need to weight up the respondents to represent the dropouts in our sample as well. The last thing we needed to account for is the population dynamics, because sometimes the population of interest can change due to mortalities or new entrants. So it depends on what is your target population. We can use what we call like the calibration adjustment to calibrate your sample data to the population of interest. So you can see weights are crucial for adjusting all these issues and make sure that the sample aligns with your population and in order to produce unbiased estimates. All right. So now I will show you how we can construct the weights so we can magically account for all these very complex issues altogether. So first, let me just walk through basic steps in weight constructions for the first wave for your initial cohorts. Actually, that weighting process is also the same weighting process when we are weighting up a cross-sectional study. So there is not much difference there. But the general process for constructing probability sample weights for the first waves includes 4 different steps. The first step is what we call compute the base weights for all the sampling units. So this is the same, the base weights actually it's the same as the design weight. So basically to reflect the study design. The second one is to adjust the weights for units with unknown eligibility. So a lot of times, like when we have a sampling frame, not every units there in your frame are eligible for your study. For example, NLSY, I have a list of all the addresses in the US, but only like 14–15% of the addresses have the eligible youth that I'm interested. So that means a lot of units are ineligible, but I don't know, right? Like whether or not they're eligible or not. So the weights, there is an adjustment to adjust for the eligibility. The third one is called adjustment weights for non-response. So this is to account for like eligible non-respondents in your sample. And the third one is calibrated to population controls. So this is a very powerful adjustment that when you know some population facts, you can or auxiliary variables, you can really incorporate those information in this last procedure. So for example, after all these other, after the first 3 steps, when you are checking your gender, the weighted distribution for, gender or race, ethnicity, and then you compare that with the population known distribution, you see some differences. So calibration can actually help you to align your sample with those known population, what we call control totals. So the sample distribution can be aligned with those known population totals. So these steps are designed to move from the initial sample selections to a final analysis files that is representative of the target population. And in order to construct high quality data, we typically will do quality control in each groups. So this includes like reviewing the weighted distribution, checking the weighted frequencies, and then compare with the external totals to see if that makes sense. I will talk about, how to make subsequent weights later, but to just compare it, to address it here is that the, first waves have these 4 different steps. And if we're waiting for the subsequent waves, the base weight, the starting points, then will be just carries forward the final weights from the previous wave or from the first wave. So you don't need to start from here anymore. You kind of start from, the final weights from your first wave. And then you do additional non-response adjustment to adjust for panel attrition. So these are the respondents who responded at wave 1, but failed to respond in later waves. So you need to adjust to account for those non-respondents as well. So that's for the non-response adjustment. And after all these adjustments, then you can do calibrations to align the weighted sample distribution of key characteristics with known population distributions. And sometimes you can also incorporate changes due to population dynamics. For example, I have new members coming into my population, or I have my members deceased or exits from my population. So you can also account for those factors as well. Okay, so we are going to get into a more like a mathematical discussion by now. So this is a mathematical section in this talk. So the base weight is also known as sampling design or selection weight. So when somebody is like talking about those phrases, they mean the same thing. So the base weight is really the inverse of a unit's selection probability. So let's denote that as pi I. So the base weight is really just the inverse of the pi I. So the selection pi I means the selection probability for the ith sample member in your data. As you can see, its primary purpose is to account for unequal probabilities of selection inherent from your complex sampling design. So for example, like NIMLAS, they oversampled Black and Hispanics. So the base weights can reflect their influence of these overrepresented groups to match with their true population proportions. So base weights are the foundation step in the weighting process. And then later that can be adjusted for unknown eligibility, non-response, and calibration. If somebody is just doing a simple random sample, the base weights basically is just their population size divided by their sample size. So for example, if I'm randomly selecting like 1,000 students from 10,000 students on my roster file, then each of them has a weight of 10. So that you know, those 1,000 students can represent all the 10,000 students. But if they are doing some stratified simple random sample, so for example, when I'm selecting students by gender, so I have 5,000 female in my sample, and I have 5,000 in my population, and I have 5,000 male in my population, and I wanted to select maybe 2,000 female and 1,000 male. So there are some variations in the sample size. So that's why we could use like the base weights should be calculated within each strata. So for example, I'm selecting 2,000 females from 5,000 females. So that will be like 2,000 divided by 5,000. And similarly, that we could compute the selection probabilities for the male as well. So you just compute the base weight just by different strata. So that's how you can do it. And sometimes this is a very popular sampling methods as well, called probability proportional to size. So for example, when we are selecting areas for household surveys, so we wanted to make the probability proportional to the population size. Or when I'm doing an education study, maybe I wanted to let the probabilities to select the schools to proportional to the school size in terms of the number of students as well. So the base weights that way is basically looking at the sum of all the sizes divided by the sample size times their SI. So that's how their design weights can be computed. So a lot of times people could do multi-stage sample. So many complex surveys could involve multiple stages of selections. For example, they will select primary sampling units, PSU first, then segments, then household. In this case, the weights should be computed for each stages of their selection, and then these individual stage weights are then multiplied together to construct the final element level base weights. So this is crucial to reflect the cumulative probability of selection. So for example, we select the PSUs, and what's the probability to select these PSUs? And then within that PSU, I'm going to select this segment. So what's the probability to select this segment? And within that segment, what's the probability to select that households? So we needed to account for all these selection probabilities. So that's why we needed to compute the the weights at each stage, and then just multiply them together to reflect the complex sample design. So for example, here I'm doing just showing an example of like two-stage design. So at the first stage, we're selecting the PSUs using PPS sampling. So for example, the weights should be the sum of all the students in that, in the entire population divided by M times SI. So the SI is, the number of students in that school. So this will be the weights for, selecting the PSUs. And then the second stage is to do a simple random sampling of the B, for example, students from each PSU. And then for the second stage, the weights really is just a number of students in that PSU, that PSU divided by the B students. So I'm selecting, B student from the SI. So the overall weights, it's just, multiplying those weights from two separate stages together, so we can get the final base weights for the design. So that's how we can compute the base weight. And after we did the base weight, we will do adjustment for unknown eligibility. So why we are doing it is because some of the sampled units, we don't know if they are eligible. So we needed to avoid like representing the target population. What we can do is we can redistribute the weights from the unknown eligible sampling units to the known eligible. So in order to understand about how to do this adjustment, we can divide our sampled units into three different groups. The first group is what we call non-eligible. So these are confirmed in the target population. The second group is called a non-ineligible. So these are confirmed not eligible for their study. And the third one is what we call the unknown eligibility. So this status is uncertain. For example, in NLSY, we selected like 100 or 200,000 households in the US. And actually, we go to the households. Some of them refuse to give us any information. Like if we ask during the screening interview, we could ask them, oh, do you have a adolescent, aged 11 to 16? And they could, some of them will say yes, some of them will say no, and some of them will refuse to answer that question. So those households said yes. So we know, oh, they are non-eligible. Some of them said no, they are ineligible. But for those who didn't, respond to that question, they all fall under the unknown eligibility. So the goal for the weights is that we needed to redistribute the weights from the unknown eligibilities to the known eligible. And in order to do that, we could first estimate the eligibility rate among those with a known status. So for example, I have 1,000 household told me, yes, I have an eligible youth. And then I have another 4,000 told me, oh, I don't have eligible youth in my household. So you could calculate that eligibility rate, and you can get, okay, so my eligibility rate among those who responded to my screeners, 20% of them are eligible. So I get the estimated eligibility rate. And after that, we could do adjustment that we could get the sum of the base weights for those known, for the known eligibles. We can do the eligibility adjustment within a cell. So for example, I know that for rural areas and urban areas, I know they have different eligibility rate. Like in urban areas, maybe the eligibles are higher, and the rural, the eligible rate is lower. That we could do adjustment by different cells as well. So within each cell, we can calculate, okay, this is my sum of the base weights for the known eligibles, and I can estimate, and I can compute what is the sum of base weights for the unknown eligibility. And because I can calculate, I can estimate my eligibility rate among those known, right? And then I can apply that rate to the unknown eligibilities to estimate how many of them are actually eligible, based on the known information. So if I sum up those together, that should represent the total number of estimated population that could be eligible for my study, right? So one component is those that know. Another is among the unknowns, how many of them are actually eligible, and divided by the sum of the base weights for the known eligibles. So you can see that now I can distribute all of the unknown eligibilities to, for those that could be eligible, I can distribute their weights to the known eligible ones to let them to be represented in the sample. So how we can do it is then we can compute or adjust the eligibility adjustment weights called WI star. It equals to WI times this adjustment factor. And then for the known ineligibles, because they are ineligible for my study, so they should have a weight of 0 because they shouldn't be, they shouldn't represent anyone in my population. And then we can exclude all the unknown eligible cases because they are, they've already been represented by the known eligibles using this adjusted weights WI star. So here is an example, a simple example inspired by NLSY. So suppose that we selected 1,000 households from the US population, and we wanted to interview youth aged 11 to 16. So we could have found that, okay, so 150 of them are eligible, and then 450 of them are ineligible. And then we still have these 400 households who refused to tell us, so they are unknown eligible. So in order to estimate the eligibility rate, we can just use the first two numbers. So the estimated eligibility rate will be 150 divided by the 150 plus the 450. So that gives us 0.25. So 25% of household have this eligible youth. And then I can estimate that, okay, so among the 400, there are about 0.25 of them are eligible for my study. And then I distribute all of their weights to these 150 no eligibles. So that means the no eligibles not only needed to represent themselves in the sample, they also needed to represent 0.667 of the eligibles among those unknown population, unknown eligible sample units. So that's why after the adjustment, they in the sample, they represent 1.667 eligible units in the sample. So we could adjust the base weight by multiplying each known eligible weights by 1.667 in order to do that. And as you can see that now, the known eligibles now represent 150 of themselves plus 0.25 times 400, which is the unknowns. So they can represent 250 eligible cases. And as you can see that because we selected 1,000 households, so 25% of them are eligible. So that's about 250 eligible households at total in this sample. So we are kind of reallocating these 150 cases to represent the 250 eligible cases. So that's the eligibility adjustment. A lot of times in longitudinal study, because we wanted to find like a particular cohort. So it's very important for us to kind of know there is a step here to do eligibility adjustment, because some of those researchers ignored about this fact. And, in that case, they will, if they're not doing it, they're kind of consider all 1,000 households are eligible. If you are not, adding these steps there. So anyway, so it could, or sometimes it depends on how they are doing the weighting, or they could only let the data, they will also consider their own only 150 cases out of 1,000 households are eligible. So that's a huge issue that they can't account for without this adjustment step. Okay, so non-response adjustment. So the non-response adjustment is always a challenge for longitudinal studies. The longitudinal studies are typically subject to two main types of non-response. One is called unit non-response. So these are individuals fail to provide data for the entire waves. And another is item non-response, when the individuals responded to most questions, but skip particular ones. So attrition is a significant threat to panel studies. So sometimes it can severely reduce the effective sample size. For example, a very well-known longitudinal study called the panel study for income dynamics. They lost nearly 50% of their initial sample by 1989 after about 20 years data collection. So the high attrition rates can lead to representative sample unless you account for those attritions. And there are typically two patterns for non-response. One is called a monotone, so which means that if somebody dropped out from the panel study, then they permanently will be dropped out. Another is called like intermittent. So some sample members, they can drop out in some of the waves, but then they will come back later in some of the waves. So they have these Swiss cheese patterns. So for longitudinal studies, it depends on the study design. So you could see response patterns in both ways. And that could, affect the way that you are analyzing your data as well. And so for when we are addressing for non-response, we need to consider, we need to make some statistical assumptions when doing those type of adjustment. So the way missingness is related to other data dictates how it should be handled. So one thing, a big assumption underlying to the non-response adjustment is that we assume that the data are missing through a stochastic process. And the stochastic process means that it assumes that every unit has a probability of being a respondent or non-respondent. So that's why we could address the non-response, the data missingness through some type of statistical process. Otherwise, if you just are thinking that missing data, missing data mechanism is non-random, then it will actually cause a problem into like a non-probability discussion, and that's a totally different subject. So when we are thinking about missing, like how data are missing, there are three different kinds of mechanisms. The first mechanism is what we call missing completely at random. So this means that the probability of missing data has no association with either observed or unobserved data. So if we translate that into non-response problem, that means the respondents are a simple random subsample of the initial sample. So the analysis on actually missing completely at random should be unbiased. So this means that everybody in your sample has an equal chance to be missing, and that's just like a flipping a coin. So for example, everyone in your data has 0.5 chance to be a respondent and 0.5 chance to be a non-respondent. So it's like a flipping coins. And then if you have 1,000 cases in your sample, and then 500 of them will respond due to this very simple missing data mechanism, there is no, this won't introduce any bias. So this is a very, very ideal mechanism, usually not very realistic in the real world. The second one is a very typical assumption or mechanism that we will assume when doing non-response adjustment. This is called missing at random. So this means that the probability of response depends on observed variables. These are typically auxiliary variables like X, but not on the missing values themselves. This could mean that a response model can be formed based on those observed auxiliaries. So many of our weighting adjustments actually assume that the data is missing at random. So this means that, in my population, I know that how the response propensities or the probability for them to respond really depend on some of their characteristics, like their race, ethnicity, their education attainment, their social economic status. So we assume that the probabilities are associated with those variables, but conditional on those variables, they should have the same probabilities to respond or not. So that's usually the assumption that we will make for a non-response adjustment. The third one actually is a very challenging one, and this is for more advanced statistical discussion, is when the missing is not at random. So this means that the probability of the responding depends on one or more analysis variable Y's. That we can only observe Y's, the respondents. We don't know the Y's for the non-respondents. Then that can actually cause biased results, right? And we couldn't fix that just based on the X variables, because that's the part that is challenging and often required some untestable assumptions in order to address this. So for my today's discussion, I will be more focusing on addressing missing at random. What's the time now? So it's already 11. Let's take a break, and then we will come back and continue talking about the non-response adjustment.
Thanks, Dan. Does anybody have any questions right now? I don't see anything in the chat so far related to the construction pieces here, but does anybody have any questions right now if you'd like to unmute yourself before we take a break? Let's see. Yes, so the slides and the recording of the webinar will be available later. Right now, Rebecca, the slides are available on the NIMLAS website that was shared earlier, so you can download the slides from the website right now. They're only going to be available for about a week, so make sure to download them right now. The recording will definitely be posted after we have processed everything. So the recording will be available for download and viewing on the NIMLAS website. So, yep. Okay, any other questions before we take a first break here? Okay, thanks, Alden. Yep. Okay, let's take our break and we'll start back up shortly.
All right, thank you. Okay, so I will come back and talk about the non-response adjustment part. This is a very interesting part in weighting. Because non-response can lead to bias in population estimates if respondents differ systematically from non-respondents. And if we wanted to put that into a mathematical way, then we can actually show that the bias of the respondent mean actually is approximately equals to like the covariance between the survey with variable y and then the response propensity phi divided by the phi mean. So this means that the bias is a function of the covariance between the survey variable and the response propensity. What does it mean? For example, if I'm doing the mental health surveillance study, we wanted to do a clinical interview to assess whether a sample member has mental health or not, any mental health issues or not. And so if somebody has mental health issues, they will be very interested to get a free clinical interview to assess their mental health issues, like what particular problems they will have. But for those who are mentally very healthy, they are like, oh, I don't really need to do any clinical interview. So they will refuse to do it. So the problem that we will see is that, okay, so somebody who has mental illness will be more likely to participate versus those who are healthy. And if we are looking at that bias, then it will, if we're not accurately account for that, then our estimated prevalence rate of depression, mental illness will be much higher than the general population, because of those with the issues tended to participate to respond. So that's why the bias is related, is a function of the covariance between the survey variable, like having mental illness, and the response propensity, right? But if y and the response propensity are not correlated at all, like when their covariance equals to 0, so that actually then we don't have any bias issues. So that will be ideal. Okay, so sometimes people will say, oh, my response rate is very high in my study. I don't need to account for it. But sometimes high response rates alone do not guarantee the absence of the bias. So for example, like in ad health, it has a pretty good response rate, but we noticed that, for example, sample members with with education lower than like attended college, so like high school degree or lower, they tended to have a much lower response rate than other sample members. So if you're not accounting for them, that's also an issue when you are doing your longitudinal studies as well. Auxiliary variables that are available for all the samples, this means include non-respondents, and respondents are very crucial for us to explore and reduce non-response bias, because especially if they can predict the survey variables or the response. And let's go. Okay, so that leads to the idea to do propensity score adjustment to handle non-response. The propensity score here means the response propensity score, which is describing the probability for sample case to respond to our survey. So that could the common process for this adjustment involves.
No. No. Esa es la otra Fer.
Hi, Fernanda, can you mute yourself? Thank you. Yep.
Okay. So one common process involves, first, we needed to fit a model to predict the response based on available covariates for both respondents and non-respondents. So for example, we can use a logistical regression to do that. So this is your sample file. So you know these some sample members responded, and these sample members didn't respond. So you can create a response variable called like R, and then you can use covariates known for all these sample members. For example, if you know their gender, their age, so you could use those to predict that. And when we are, for example, doing household surveys, we know, okay, this household is in this state, or is in a rural area, urban area. So we have know something about this household, so we could use those variables to predict the probability for that household to respond or not. So this is a model to predict a response based on available covariates that are known for both the respondents and non-respondents. And based on that, we can sort the file from low to high based on the estimated response propensities, basically based on the predicted response propensities from a model. And then we can divide that into cells with the equal number of sample members. So typically it could have like 5 to 10 classes, 5 to 10 cells. And then within each cell, we compute what we call non-response adjustment ratio. There are two different versions that typically survey statisticians can do. One is called a weighted ratio, which is a sum of weights for all the sample in this cell divided by the sum of the weights for the respondents. So I just calculate a weighted ratio. Another one is I can do a one-weighted ratio. It's just looking at the total sample size in this cell divided by the number of respondents. And then at last, we could multiply the weight of each respondent in the cell by this non-response adjusted ratio. So this will be what we call non-response adjusted weight will equals to the WI star, like after the eligibility adjustment times this ratio. That will be like the non-response adjusted weights. And after this step, only respondents have a non-zero weight, because we're weighting up the respondents to represent the non-respondents in the same cell. So that's why only respondents have non-zero weight, and then we can let all the non-respondents to have a zero weight. So somebody may ask why we are using cell instead of just using the predicted response propensity directly. Like I can just build a logistic regression to predict everybody's response propensity and then apply that as a non-response adjustment. One of the advantage of it is really that it can help us to stabilize the adjustment and control for the variance. So if you just take the inverse of the predicted response probabilities as a direct weight adjustment, it's okay, like statistically, that's correct. But sometimes if we have like extreme or poorly estimated propensity, it can really blow up the weights. So for example, what if in your logistical regression, some of the response propensities are like 0.005. And if you take the inverse of that, it's 20. So that means you needed to inflate the weights 20 times bigger in order to account for non-response. So sometimes that can cause like too much dramatic weighting adjustment. So the cell adjustment will be causing a more smooth adjustment. So that can smooth over model noise and avoid excessively large or unstable weights. And also, forming the cells can be more robust to some of the model misspecifications, because when we are using logistical regression or other modeling techniques, it's an approximation. So if the model is slightly wrong, then the predictions can actually inject a systematic bias in your adjustment. So that's why typically we recommend people to cluster the cells and then to apply the rate adjustment using the cells. Another way, which is a more popular way, I think, like, I'm seeing people are doing right now, is a revised non-response adjustment. This is based on the classification and regression tree. So the process is very similar, but instead of fitting a logistic regression, they can fit a regression tree to predict the probability of response using available covariates for both respondents and non-respondents. So if you know a little bit about the regression tree analysis, it's kind of recursively trying to partition the sample into subgroups that differ in response likelihood. So for example, okay, I may detect if I separate the sample into education levels, they have different response patterns. And if I separate the groups further based on their incomes, that can actually separate their response patterns. And then each node, it's like the tree leaves. Each node is a cell. For each node, we could actually compute the non-response adjustment ratio. So that's similar to what we've done before. So in each node is like the adjustment cell. So the sum of the weights for the full sample divided by the sum of the weights for the respondents in that node, in that cell, will be the weighted ratio for adjusting the weights. Or you can also compute an unweighted ratio. And then you can multiply the weight of each respondent in a cell by this non-response adjustment ratio. And after that, only respondents have a non-zero weight. So you can see that, there are more and more machine learning algorithms that can be used in this process to model the response propensities. Like the regression node, why I think sometimes it has a little bit more advantage than logistic regression, because it has a very reasonable way to create the cells. Rather than logistic regression, you just sort of divide it into 5-10 cells based on the size. So maybe some of the cells are more similar to each other. Some of the cells within them, there are some differences. So you can't really account for that. The tree, when they're growing the cells, each cell has a particular definition. So I think that's why, the more and more like the regression tree analysis and other machine learning algorithms are being used for non-response adjustment, because they have some other advantages. So here is like just showing you an example about, using the regression tree to do non-response adjustment. Is like, after the tree analysis, maybe we can see like, for the entire sample size, there are 20,000 response rate is 50%. And the tree first will find, okay, for female and male, their response rates are different. And the female has 10,000 and the male has 10,000 in the sample, and they have different response rate. And after that, we will find maybe within female, another big distinguisher here is the urban-rural status. So for urban, they have a much higher response rate, and the rural, they have a much lower response rates. So after you break down your sample this way, then you can say, okay, among the 9,000 urban female, their response rate is 5.71%. Then I can use my adjustment ratio as like inverse of this 65% as my adjustment factor. And for female rural, then you can use the inverse of 30%. So you can see that the inverse of 30% is larger than inverse of 65%, right? So we are adjusting the rural female respondents more in order to represent the 3,000 samples in this cell, because this is a low response cell. We need to weight up them more in order to represent all the sample cases in this cell. So that's the idea. And similarly for the male, the response rate overall is 45%. And maybe the next distinguisher is not rural or urban anymore. It's about education attainment based on the regression analysis. And then we could see, we can adjust the non-response within each cell as well. So that can help us to more accurately address these non-response issues based on different auxiliary variables. So that's the advantage for the regression tree. As you can see, it forms the cells in a very nice, with a very nice definition. Also, it could account for some interaction effects into the consideration as well. So now it comes to the R practice. So if you can download the course materials, I included both files in my, in the course materials. Depending on your R level, you can, try to run those R code by yourself, or you can just looking at the HTML file, which has all my outputs. Okay, so let me share my screen with the outputs, and we will talk that way. Okay, so here is an R example for us to see how it works to do non-response adjustment using regression tree. So the method actually is that we will fit a tree to a binary response indicator. So R will equals to 1 for respondent and 0 for non-respondent. And then we will use the terminal nodes, or sometimes we can call that as leaves, as the adjustment cells, and then we can inflate the respondent weight within each cell to represent the full sample to account for those non-respondents. So this method, first we will fit the regression tree for these response indicators using the available covariates. Then I will use the leaves as adjustment of cells. And in each leaf, we could compute the non-response adjustment ratios to kind of get the sum of weights for all the cases in that cell divided by the sum of the weights across just the respondents in that cell. And then we can multiply each respondent's base weight with this adjustment ratio. At last, we always do some quality control checks, right? So we could verify the mass preservation, which is kind of compare, okay, this is my sum of the weights before adjustment, and this is my sum of the weights after adjustment. To clearly show you how this it actually is being done, so I just simulate a data set for us to use. This is a data called DAT, and it has a sample size of 2000. Sorry, my mouse is funny. Okay, and the data frame has variables. I created age, which is a random variable between 18 and 70, female, income, urban, and then I created a variable called a prior, or which is reflecting the prior wave response indicator. So this is typically like in longitudinal study, the prior wave, like whether that cases responded in the prior wave is always associated with the response propensity in the current wave. So I also just randomly created a variable for the base weight to kind of just for demonstration purpose. And now I wanted to model, like I want to generate a true response propensities and then generate, observe the response values based on that. So what I did is I used a logistic regression kind of format to, making the linear functions that will be associated with all these variables, all these auxiliary variables I generated. And then I produce the probabilities based on, this linear function. And then I generate the response variable R. So R equals to 1 or 0 based on this probability. Okay, so you can see that, the truth underlying is the response propensities are associated with those variables. So here you can see these are the summary of the data for different variables. So this is my age distribution. So for female, mean is 0.51, so about 52%, which aligns with how I want to generate it. Income, urban, prior wave, the mean is like 59%, 60%. And this is the R, the response rate, the response indicator for the current wave. So like around 30% responded. And the W is the base weight. Okay. So I have my covariates. I have my R, which is the response indicator for the current wave. I have my base weight. So the first step I need to do is I can fit a regression tree. And then now in R, you can use this package called rpart. And you can install the package if you don't have it. And then you can run the tree analysis. So suppose that the response indicator is my dependent variable, and I put all these covariates in my model. So these covariates, I know them for all the respondents and the non-respondents. And I can use like method called ANOVA to analyze the variance. And I can put some control there. So let's say, I can control for some of the parameters for the model tuning. And also I can define what is a minimum bucket. So this is kind of defining how small, because I don't want to have too small cells in my tree analysis. When it gets to when the cells are too small, it's easier for us to get some extreme the predicted values, right? So in order to stabilize that adjustment, I wanted to make sure my cell size is adequately large. I have enough cases there for calculating a meaningful ratio. And you can see that, when doing the nodes, then it can, split the data based on different variables. And I can make a visualization using rpart dot plot function. And you will see like a tree analysis like this. So the first, most important factor here is whether they responded in the previous wave. So if the prior R equals to 0, which means that they didn't respond in the prior wave, then that, cell within that cell, about 26% of them responded in the current wave. And versus with those that responded, so the prior R not equal to 0, about 33% of them responded. So you can see the difference, right? The tree can pick up the difference, and the tree basically is identifying this as the most significant factor. And after that, under those who responded in the prior wave, then income becomes a big factor. So it can help us to, find the response rates within each cell, and then we can do adjustment using the rates. Okay, so now we've already identified the terminal nodes, which are, if you look at the tree, basically these are the final nodes. So we have like 3 groups here. You may say, hey, wait a minute. I know that you have more covariates then just the income and the prior art. You also have age, female, and urban, right? But the tree is trying to see what are the biggest distinguishers. And after that, there are some differences, but the differences are small. And if you go back to my model, you can see why. Like age only have like 0.01 effects, and although like gender has a pretty big effects, maybe after accounting for other variables, it becomes to be less significant. So, something like that. So after the nodes are identified, the tree will output the nodes into a variable called where. So you can define that as the leaf ID. And then I can set this leaf ID as an integer. And then I could, within each leaf, I can use the aggregate function, for example, to compute the sum of the weights. And so I can get the sum of the weights across all the units and then subset it to only respondent and then get the sum of the weights for the respondents. And then I could merge those two together and then compute the adjustment ratio A, which is the sum of the weights for all the sample units within each leaf by leaf, and then the sum of the weights by the respondents, and then you can see a data like this. So I have the sum of weights for all the units and the sum of the weights for respondents, and the adjustment of that factor is basically this variable divided by this variable. So there are 3 different nodes. So I have nodes 2, 4, 5, and we can, so these are different cells. So you can see we can compute the adjustment of ratios based on, by these cells. And at last, we can merge it back to the main analysis data, the DAT data, and then you can see that, okay, so these are the variables I generated before. This is the base weight. This is whether they responded or not. So this is my adjustment rate based on, the definitions for the leaves. So for example, that will be based on prior R and the income, right? And then based on that, then we apply the A with the A times the W will be the adjusted weight. So, and the adjusted weight is only non-zero for respondents. And for non-respondents, as you can see, their weights all becomes 0. Okay, so this is how you can, do regression tree analysis and then do non-response adjustment that way. And after that, sometimes like we can do some QC checks. So one check that we can do is within each leaf, we can check to see, okay, whether the adjusted response weights should sum to the original total weight in that leaf. Because the idea is that, right, that I weight up all the respondents within each leaf in order to represent all the sample cases in that leaf. So to compensate for those that can't be, represented by non-respondents. So you can see that after the adjustment, the sum of the adjusted weights actually equals to the sum of the weights before the adjustment across all the sample units. The difference, we can compute the difference. And the difference is almost 0 for each leaf. We can also check, okay, whether the adjusted response weights equals to the original total weight for my entire sample. So I can just sum up all the weights together to compare it, and you can see that there is no difference as well. We can also just check to see, okay, what is the estimated propensity for each leaf in that way, we could like just compute what is the average value of R, the response indicators within each leaf, and it will give us like, some rate informations there as well, because I only have 3 leaves. And if I call out to give me the first 10 rows, it will give me a bunch of missing values. Okay, so last, just some practical tips is that first we could using like pruning or increase minimum bucket to avoid the tiny leaves, to avoid like unstable ratio adjustments. And we can consider trimming very large adjustment factor AC to control the variance. So if you are seeing like, okay, particular leaves have very large adjustment factors, and that may cause extreme weights later, maybe you can go a level above. So it means that I don't want to split that tree too much. Let's go to the level above and see if the adjustment ratio can be tuned down. We can also include like design variables and frame element covariates in the data if available. So for example, if you have some stratification or clusterings in your design, you can also add those as covariates for non-response adjustment as well. And also if you have some administrative data that are known for both the respondents and the non-respondents, those are useful to be incorporated in the tree analysis. The nice part for tree analysis is that you can give it 100 or more candidate variables. It can help you to select which ones are important for you. So you can just throw all the variables into this modeling process, and it will help you to select the variables. And after adjustment, we can proceed with the a survey analysis with the adjusted weights. And I will then get into the calibration process, which will be the last process for the weighting process. Let me pause here and see if you have any questions, maybe.
Bob has a question in the chat. Before we get to that, though, I just want to kind of underscore, I mean, some of you may not be responsible for actually constructing the weights in this way, but I think this is a wonderful example of the work that goes into creating these weights and calculating appropriate adjustments and so forth. So this kind of doubly emphasizes the need to use these weights, because you can appreciate how much work goes into making sure that you're correcting for these different sources of bias, making sure we're adjusting for all parts of the sampling process. This just really gets under the hood and shows you all the work that goes on. So we just never want to completely ignore these weights, especially in longitudinal studies. This is just so valuable. So thanks, Dan.
Mm-hmm.
Yeah, so Bob says, Dan, the regression tree example is great in improving my understanding of how weights are constructed. Given that many data sets provide weights to users that take such processes into account, do you recommend that users try to improve weighting on their own beyond what's already provided by a particular study? Or do you recommend that users just read user guides carefully to understand the construction of weights, but without their own weighting adjustments applied?
This is a great question. I think it depends. If you give the data to me, I can say, oh, I can, improve the weights, especially if I know a particular analysis that I'm doing, like what is my Y variable, right? So I can first assess, okay, whether my Y variable is really correlated with the response propensity. So I could kind of re-engine some of the weightings to just thinking about how I can improve my estimation for this particular analysis. But a lot of time, as you can see, there's a lot of efforts that you need to make those weights. And so that's why typically we don't recommend the users to just construct those by themselves, because there are also a lot of considerations going on as well. So that's why we are trying to make the weights to, for example, when doing non-response adjustment, we're trying to incorporate all these useful covariates to make the weights more general to be used for different purpose. So I think it really depends. So one thing is that typically when we are thinking about addressing missing data, we can use either weighting or imputation. And some people, like when we are doing imputation, then we need to impute each y variable, which will be also a lot of work for people to do. So that's why we recommend using weights, because weights can be used for all the different variables.
Yeah. And Bob, I would add too, like as a data user, you typically don't see information for the non-respondents. Like remember in Dan's example, she simulated a whole bunch of data for non-respondents that she could use to compute these predicted probabilities of responding. So as a user, kind of developing your own non-response adjustments without seeing data on the non-respondents is usually off the table. So all you really have at your disposal is some kind of additional calibration adjustment or something like that. So that's another complication as to why like all these steps are taken to make sure that all the user has to do is just use that final weight in the actual analysis. And this is why when we see studies that ignore the weights entirely, we're just like, what? Like it's a real head scratcher. So yeah.
Great, thank you both. That totally makes sense. Yeah.
Okay, Yvonne says, what would the approach be for a study that is a repeated cohort panel? So for example, the first cohort in 1976 is followed over time, and then there's a new cohort every year thereafter. So respondents range from age 19 to 65 based on the cohort with new data collection every year. Would you be recommending a tree model per cohort per data collection year, or one tree model per data collection year across all the cohorts?
Yes, so sometimes when you are dealing with a complex design like this, I would recommend you to kind of, set the sample separately. So you have your first cohort in 1976, right, followed over time. So for that cohort, you can really model their response propensities. And then you have a new cohort every year thereafter. So you can also model the cohort separately. You wanted to model them together. If you wanted to model the true model, if you wanted to do one tree model per data collection year across cohorts, that works as well, but you are making assumption that there is no different. And one way actually you can do it is you can also add a cohort as a covariate in your model, in your tree modeling, and see if that tree will, pick it up and see, oh, maybe different cohorts has a different response rate or not. So that's one way you can think about it. So this is actually reflects in like this part and include design variables into your tree.
Yeah, and she said, thanks. We've traditionally modeled weights separately by cohort, but didn't know if a group model would be possible. So yeah, I agree with what Dan's saying. Probably best to allow for heterogeneity across the cohorts in terms of what matters.
Okay.
Okay, thanks. That's all for the chat. So.
Okay, so share my screen again. Okay, so the next step is calibration. This is a very lovely step. I really like it because it's a step that not only can help us to reduce the bias, but now can also reduce the variance. And this is because we have some external information that we can leverage through weighting. So calibration is really helping us to adjust sample characteristics to match with the known population totals. So it can reduce the bias because we have this, very useful auxiliary information. It can also correct a coverage error, which is like a bias. So this could be like certain segments of the population might be under or over represented in the sampling frame. And these methods requires population totals of the auxiliary variables X. And the X could be for individual responding sample units. The nice thing is that it doesn't really require X for individual non-sample units or non-responding sample units. And like poster stratification and raking are common examples of calibration. So what this means is that we need to know the X variables for individuals responding sample units. So we need to know that for every respondent. We also need to know the population totals for those variables. We don't need to know the X values for all the individuals that are non-respondents or not selected in the survey. So for example, if I'm doing calibration to calibrate my respondents sample to the population in terms of sex, so I know, okay, according to census data, this is my gender distribution in the population, and this is my weighted distribution in my respondent weights, right? After non-response adjustments, I see they're different. So I can calibrate my sample weights to meet with those population totals. I know that the population totals is true. So this is what the calibration means. So sometimes for our target population, we could the blue part can be our target population, and the population that we're doing the sampling could be the yellow part. And the middle part is what we call the eligible sample covered population. But sometimes the sampling population could have over coverage issues, like the sampling population could cover some units that are not really in our target population, and we don't know. And sometimes the part of the units in the population could be not covered by my sampling population. So the calibration is trying to match my sample to match the sample to align with the target population to compensate for both over and under coverage. The post stratification is a simple calibration method. So we just group the sample and the respondents into post strata. For example, we can group them by age, region, or other demographic characteristics. Then we adjust the weights so the estimated count of units in these groups match with the known population control totals. And then we could apply that to my final weight, apply that to the final weight. So the post-stratification weight equals to my non-response adjusted weights times the NY, which is the population count for the post-stratum Y, divided by just the estimated population size based on the input weight, which is the WINR. And I will show you how to do that in our practice example. So you can think about, okay, so in my population, I know that there are 5,000 female in my population, according to like a school roster, for example, if you are doing an education study. But based on your sum of the weights of the non-response adjusted weights, you get the estimated count in your sample is actually 4,000 females, but you know they're actually 5,000. So you can say, okay, my adjustment factor is 5,000 divided by 4,000. I inflate that weight. So the sum of my post-stratification weights will be equal to 5,000, which is a population total that is known for my study. So the term, this ratio term is what we call the post-stratification adjustment factor. So this method is very effective to force the weighted sample distribution to match with the known population distributions for their chosen demographic characteristics. So here is the example. If I sum up, so this is my post strata. So I have 8 different strata here. Then the sum of my non-response adjusted weights is like this. But I know that my population, my target population total has this different accounts. Then I could calculate the adjustment factors. So for example, in my population, I know there are only 4,500 cases in this first strata, post strata, but my sum of the weights is 5,000, so I can adjust that down. And then after the calibration, after this adjustment, the sum of my weights will be 4,500, which aligns with the population. So you can see how I'm calculating the adjustment factors based on the population totals divided by the sum of the weights, and to get the adjustment factors for each strata. Apply that to adjust my non-response adjusted weights. So the sum of my calibrated weights will agree with the population known totals for each strata. In R, we can actually use a stratify function to do post stratification. You need to tell it's under the survey package. So this is a pretty big package to do a variety of different things for survey data. So you need to tell it what's the design, what is the strata, what is the population. And so I provided some information there. The second approach is what we call raking. So raking is when you only have marginal population totals for several factor controls like age, sex, but not jointly. Like, okay, I have a data. I know according to census data, this is their total counts of people by age. These are the total counts of people by sex. But I don't have the joint distribution. But I wanted to incorporate all these counts. How I can do it is raking can do an iterative procedure, kind of like I match by age first, and then I match it by sex, and doing that several times so that you can get a converged distribution that, if you look at it by age, they align with the population totals by age. Then if you look at the sex, then they align with the population totals with the sex. So raking can also be implemented in R through a function called a rake. So that's how you can do it. The third one is what we call grade. This is more typical calibration variables, calibration model. So basically, it's like it actually uses statistical model to do similar things as post stratification and raking. So it incorporates all the variables that you want to calibrate to as X variables, and then you regress the you can regress the survey variables on all the calibration variables, and then you can do the calibration this way. So this is like, I don't have a lot of time today to go through details about how rake works, but basically the nice thing about this approach is that the calibration variable in this procedure can be either categorical or continuous. So you can just use one model to calibrate the sample so that the weighted sample distribution can align with the population distribution for all these X variables. So that's why we are calling this as a calibration variable. So especially sometimes, like when we are doing longitudinal studies, we have a lot more information about respondents and non-respondents from the later waves. we know, their data from the first wave or prior waves, so we could use actually those variables as calibration variables to do calibration that way. So anyway, the grade can be actually used, can be done through a procedure called a calibrate. So this is how we can do calibration. And I also provided the calibration examples in my R Markdown files. And I think we should take a break for 10 minutes. Brady, what do you think? I'm thinking about skipping this example because I have other slides to go through first.
Yeah.
And they can just look at the examples by themselves.
Yeah, I think it's useful to have these calibration examples just to see how this additional step is applied in practice to be sure. But I think it'd be good to focus on like the estimation after the next break. So, yep.
Yes. Mhm. All right.
Okay, any questions before we take a second break here? Or I don't see anything in the chat, but any other questions before we break for about 10 minutes here? Okay, all right, yeah, not seeing any. So yeah, why don't we come back at about 12:10 then? Yep.
Yes.
Okay, thanks everybody.
Thanks. Mhm. Okay, let's go on. So the next section, I'm going to talk about how to share our experience on how we construct the weights for later waves for ad health as example. And then I'm going to get into discussions about how to apply the longitudinal weights for estimation. Did I skip anything? Okay, so let me see if oh, I think I left a slides out to show the structure for the ad health. So let me just talk a little bit about it. So for ad health, we have two separate subsamples at wave 6. So one is called a sample 1, another is called a sample 2. Sample 1, we did a web survey for sample 1. And then for non-respondents from the web survey, we subsampled some of them and did an in-person follow-up with them. So that's sample 1. Sample 2, we did in-person data collection. And when we're calling the grand sample, that means it's combined a sample 1 and a sample 2. The idea is that in some of the longitudinal studies, you can see that they could be doing some subsampling for their cohort later, and then do different type of treatments or analysis. So when we are constructing the weights for the later waves, we needed to consider those subsampling process as well. So here for demonstration purpose, I will show you how we constructed the sample 1 only weights, because you can see how subsampling is incorporated in the weighting. You can also see how the two-phase sampling design with the web survey as the first phase, and then with the non-response follow-up at the second phase, how that two-phase design can be incorporated in the weighting. And you can see how non-response patterns at different phases can be accounted through weighting adjustment. So let's start with the base weight. The base weight first will be the final wave 1 weight, because all the wave 1 respondents will be eligible for wave 6, except for those who become ineligible, like deceased, incarcerated, or under some specified exclusion criteria. And then after that, we need to incorporate the phase 1 selection probability. So basically to multiply the wave 1 weights by the inverse of the phase 1 selection probability to account for that subsampling. And in order to reflect the two-phase design, we actually has a much more complicated procedure to construct the weights to account for the phase 1 web survey and the phase 2 non-response follow-up. So about like 50% of the phase 1 non-respondents are subsampled for this in-person follow-up. So there is an additional subsampling that we needed to deal with in that step. And then after that, we need to do non-response adjustment and a calibration. Okay, so for the non-response adjustment, we use the regression tree analysis to do non-response adjustment. Unlike the first wave, we only have covariates from from the sampling frame. For the later waves, actually, we have more information about these sample members. For example, we found that the prior wave response indicator is a very big key predictor in the non-response adjustment. For example, whether that sample members responded at wave 4, wave 5, those are pretty big predictors on whether this sample member will respond at wave 6. So we needed to consider those information in non-response adjustment as well. And then we can add other predictors that we know for these type of cases. Then at last, we could align the weighted sample distributions with the known population distributions. And this is a step that we can also incorporate the changes due to population dynamics. For example, we know that some cases become ineligible due to death or incarcerated. So we could actually exclude them from the pool when we are calculating the control totals. So for wave 6 of ad health, for example, we can use all the wave 1 respondents. So we treated that as the base. we compute the weighted sum of different characteristics based on wave 1. And we can consider them as a better known population totals than just based on the wave 6 respondents. So we could calibrate the wave 6 weights to agree with the wave 1 weighted sum of the weighted estimates. So that's another type of calibration we can do for longitudinal studies. So, for sample 1, because we have this subsampling and we have the two-phase design, we actually constructed 2 different estimators. The first estimators is basically using the wave 1 final weights and also considering the subsampling, which will add the inverse of the selection probability for case I to be selected in sample 1. And then we add the response propensity, the inverse of the response propensity from the phase 1, from the web survey to do non-response adjustment. So with these weights, so when we are accounting for the wave 1 final weights, accounting for the selection probability for case I to be selected into sample 1, and consider, okay, what's the likelihood for this case to respond at the wave phase 1? Basically, this estimator itself can be an estimator to estimate the population total. Because this is by ignoring that we've done non-response adjustment. So this is basically an estimator that can estimate the weighted total. Another estimator we considered is actually what if we are considering about the non-response follow-up. So in that, we actually consider all the cases who responded in phase 1. We use their wave 1 weights as their we use their wave 1 weight as their response as a weight, and then we can consider, okay, what is their subsampling selection probability to be selected into the NERF, and then what is their responsibility? What is their response propensity at the NERF at the phase 2, the non-response follow-up phase? So in this case, we could consider the subsampling from the phase from the for the phase 2 for the NERF into account. One thing that I missed here is that I still needed to use the inverse of the beta 1 for these cases here. So we needed to account for both the subsampling to get the sample 1 and also the subsampling to get the NERF. So anyway, this is just a demonstration purpose to show you how complicated sometimes the weighting can get when you have subsampling and multi-phases in your longitudinal studies. And that's why survey statisticians are making a lot of efforts to make sure the sample aligns with your design. And at last, we actually have some strategies to combine these 2 different estimators here to achieve an estimator with the least mean squared of errors. So one estimator could have less variance, and another estimator could have less bias because of the non-response follow-up, and how we could make composite estimators to achieve a weight that can make the least mean squared of errors out of their estimation. Okay, so after we talked about all of the weightings, I wanted to make a big distinguish between cross-sectional weights and longitudinal weights, because a lot of times when researchers, they're using weights from a longitudinal study, they will say, oh, I'm using a longitudinal weights. And I'm always asking you, are you using a longitudinal weights? And, they really need to go back to the user's guide and see exactly what the weights are reflecting to. So there are actually 2 types of weights we typically make for longitudinal studies. One is called cross-sectional weights. So this is trying to address representativeness for the point in time estimate. So for example, I could make cross-sectional weights for wave 6. So that is to be used to make estimations for at health population at wave 6. Okay, so the respondents for cross-sectional weights are those who provided the data at that wave. So for example, wave 6 cross-sectional weights, well, you know, everybody at wave 6, if they are respondents, they have a non-zero weight. So that's cross-sectional weights. Longitudinal weights are designed for analysis spanning 2 or more waves to estimate wave-to-wave changes. And in this case, the respondents should be individuals who provided the data at all these waves in your analysis window. So for example, for waves covering wave 1, 5, 6, right? Then your sample member is considered to be a respondent only if they provide the data at each of these wave 1, 5, 6. And so only these respondents have non-zero weights. Others, they have a 0 weight, even when somebody who responded at wave 6. But if that person didn't respond at wave 5, that person will have a weight of 0. Because we are interested to measure this longitudinal change, we need to have data across all these different waves. So the steps for building the cross-sectional and longitudinal weights are similar. You can think about, okay, this is my base weights, this is eligibility, this is my non-response, this is calibration. But you can see that the respondents are defined differently when we are constructing the longitudinal weights. So that's how we can do it. But a lot of time, like, you know, sometimes you can see my longitudinal weights for my wave sets are not available. For example, I want to analyze waves 1, 3, 4, 6 because they have, you know, this variable there. But I only have the final wave 5 cross-sectional weights. How can I, wave 6 cross-sectional weights, how can I do it? Because all of your respondents is like a subset of the wave 6 respondent, right? Because you are interested in respondents who responded in wave 1, 3, 4, 6. And now you have a weights that is positive for the wave 6 respondents. So you actually can build your longitudinal weights in your own way. For that, first you need to define, okay, what is my longitudinal respondent indicator? So R equals to 1 for all the sample members responded in all the required waves. And then R equals to 0 for others. Then you can just add a non-response adjustment among the wave 6 respondents. So now you can just restrict it to your wave 6 respondents and then model the likelihood, the probability of being all wave respondents among those wave 6 respondents. And then you can use the predicted propensities to form weighting cells. And then you can inflate the wave 6 weights to compensate for non-respondents among these groups. So that will be kind of calculating the ratio, then apply that ratio to the wave 6 cross-sectional weights. So you can account for that additional non-response adjustment. And after the non-response adjustment, you can also do calibration. You can calibrate it to wave 6 control totals because the wave 6 have already calibrated to population totals in terms of like age, gender, race, ethnicities. So you can use the same controls to, you know, compute the wave 6 control totals, and then you calibrate it to that. So that in that way, you can create your own longitudinal weights with additional non-response adjustment and the calibration. Another way, sometimes when people don't have capacity to do it, is they can find like you know, longitudinal weights for like waves 1, 2, 3, 4, 5, 6, and then they can also do, you know, across waves for these waves. The only disadvantage is that you will lose more data because of when you are using a longer waves, you have less respondents who can respond, who responded in all these waves. So that's the disadvantage of using all waves, longitudinal weights. Okay, so I just want to show you, because I added those slides. So these are not on your slides, but I think it's important for me to kind of emphasize that. So for cross-sectional weights, it's basically weighting all of your respondents in the corresponding time point. So for example, for the first one, you are weighting across all these cases, and the second one, second time points, you're just waiting for respondents in the second wave. And the third one, fourth one, you can see, your sample is shrinking in the monotone response patterns, and then you are kind of waiting more and more on these respondents to do it. And then when you are doing the cross-sectional weights for this, Swiss cheese intermittent response patterns, then you are like waiting for other respondents still to represent the target population. So these could be your cross-sectional weights across different waves. But if you're looking at the longitudinal weights, so for example, if I wanted to model like some trajectories across wave 1 to 6, then you can only assign weights for this first row units because they have data across all the waves. Similarly, here you can only weight them because these are the only ones who have data across all the waves. So these are for longitudinal weights. So when we are talking about weights, another important part for us to consider is variation in the weights. Because weights can vary a lot, right? Because of the varying selection probabilities, unequal response rates, calibrations. So all of this can make the weights vary a lot across different units. So although varying weights are essential for us to reduce the bias, it could potentially help increase the variance of the estimates. So there is a trade-off between the careful of, between bias and bias correction and weight variation control. And that's why, like, statisticians invented a measure to describe the weight variation, which sometimes it's called unequal weighting effects or Kisch's design effect due to weighting. But basically, this formula, if you look at it, is 1 plus CV is square of the CV of the weight, the coefficient of variation. So when the weight has a lot of variation, the CV is the standard deviation of the weight divided by the mean, right? So when your weight has a lot of deviation, then your CV tends to be large. Then your design effect, this unequal weighting effect, will be large. But when your weight are all equal, then CV of the W should be equals to 0. Then your UWE equals to 1, right? So it indicates how much larger the variance of an estimator is compared what it would be if all weights were equal. So that's the concept for these unequal weighting effects. So actually, in my example, I will show you like in R, like prac tools can actually compute their unequal weighting effects using a function called the DEFF. So this is something like after somebody constructed the weights, they should evaluate what is their unequal weighting effect. Okay, so now we get into how we can apply longitudinal weights for estimation. And so for complex survey designs like, NIMLAS or at health, because they use the clustering designs, they have a lot of fancy features. So the standard errors are usually larger than those calculated assuming a simple random sample. So that's why when we are doing estimation, it's very important for us to incorporate the design variables in your estimation. That's why typically we recommend that somebody use like survey package to do your estimation rather than treating them as a simple random sample. Without doing that, you probably will underestimate your standard errors. So another thing is that I wanted to talk a little bit about like what is the unequal weighting effects, the Kitsch's design effect, and what is a conventional design effect. Because I found a lot of people, it's very easy for them to get confused about those two terminologies. They assume they're the same thing, but they're not. So the Kitsch's design effect basically is describing how much variation we get from this unequal weighting. And I will just showed you the formula, right? The formula is just related to the weights. So the weight variable is only input is the only input required, and it's a diagnostic tool to assess the variability of the weights. It's actually very useful because when like survey statistician creating a weights, they will be used for a lot of different things. So a very easy way for us to alarm people about the weight variation is just telling them about this design effect, Kitsch's design effect. But the conventional design effect is actually looking at the total impact of their entire complex survey design. So this not only include the weighting, but also like clustering and stratification. So it actually computes the ratio of the actual variance of a specific estimates from the complex sample to the variance of the same estimate from a simple random sample of the same size. So basically you compute the variance given all the complex design, and then you compute the variance without considering this complex design and what's the ratio. That's the design effect we talk about the conventional design effect. So it considers both like weight variables, strata, and cluster variables. So both are very important in survey statistics, but we just needed to pay attention to them. When we are like, I talked about like there are cross-sectional weights and there are longitudinal weights. Cross-sectional weights is for single wave analysis, and longitudinal weights basically is for multi-wave analysis. So when you are doing your analysis, considering about what data you want to use, you need to choose different weights. So like many longitudinal data sets like at Health, we offer multiple weight variables. So first, you need to go to your documentation and find the best sources about those weight, their purpose, and then apply them, appropriately. I've seen like people sometimes get really confused about, oh, well, why I have 5 different weights in my data set. This is, because of they are created for different purpose. So for cross-sectional weights, you can use it to analyze data from a single wave. And if you wanted to follow all respondents from a specific wave forward, and then to do some time to event analysis, you can also use the cross-sectional weights. So like when you're doing survival analysis, for example. But for longitudinal weights, it's when you wanted to analyze a subset of respondents who remained in the study across multiple specific waves. So you needed to, then you needed to find the appropriate longitudinal weights for your analysis. So when to use weights? When we are producing like descriptive statistics, we always use weights for descriptive statistics, and it's very easy. Like you can do it in the survey procedures. So the weights, as what I mentioned earlier, are very essential to ensure the sample is representative of the population of interest. If you ignore it, it's very likely for you to get a biased or inaccurate results. Like in NLSY, for example, they oversampled Black and Hispanic. So without the weights, then the results will skew toward those those group averages. But for when we're doing regression analysis, there are actually more arguments about whether or not we can incorporate weights and how we should incorporate the weights in regression analysis. I know that some of the longitudinal studies or multi-level, design, like education studies and establishment studies. So that creates some challenges to incorporate the weights into study, into multi-level modeling. And there are more advanced topics on those, how to incorporate the weights in those settings. But overall, some sources suggest not waiting for regression analysis, but include the variables used to construct the weights as independent variables in the model in order to control all the confounding effects that could be introduced by those variables. So for example, if you found your response propensities is associated with urban rural, then you add urban rural as a covariate in your model. But others really advocate for weighted regression, especially nowadays. Survey packages provided functions to incorporate weights in generalized linear models. So my recommendation usually for people who are doing this is you can try both versions and see how the results are different. Because the weights, because unlike the descriptive statistics in regression analysis, typically is interested to describe association between like y and x, right? So it really depends on how the weights can correct for some of the confounding effects, or whether they are associated with both x and y. So that's why it's a little bit different. And if using weight in regression, it's crucial for us to use correct statistical procedures to adjust the standard errors. So like in Stata, we have SVY procedures, and SAS have like proc logistic, and some other procedures. In R, we can use the survey package to account for that. Some people will apply the weights in their more like conventional statistical software. Typically, they treat weight as a frequency. So for example, a weight of 5, they assume there are 5 observations with the same value, but it's a different concept in survey analysis, that the weights is kind of a probability for that case to, reflecting a probability for that case to be, to be selected from the population, either from the selection procedure or from the self-selection response procedure. So here I'm using I'm going to show you R examples. Here I'm using a data from the AdHealth public use files. And so we have the case ID, I have the cluster ID, I have the cross-sectional weight, and I have a longitudinal weight for waves 1 through 5. For variables, I have their sex, race, body weight, medical, past 12 months needed medical care. So that is named as Medicare, and then dental care, which is a past 12-month dental care. So I can show you how to do that. Okay, so let me just show you those codes. Okay, so in this case, I needed to do this way, make sure that I'm doing it right. Okay, so first I want to show you how this data looks like. So in this data, I have the ID cluster design, that this is a cluster variables, and then I have the weights, cross-sectional and longitudinal weights, and I have all these covariates. So that's how like my data looks like. Then I can go to the practice. Okay. So first I will load some of the packages. So if you have not installed it, you can install it. And then we can read the ad house data files. And in order to for demonstration purpose, I created 4 strata variables in ad house. You know, they only provide the cluster variables. So I created 4 strata with approximately equal number of clusters. So here I'm just doing that. So I have 4 different strata here. And then because some of the variables I have missing data, so I'm also doing some random imputation here as well. So you are free to look at how I'm kind of manipulating the data, and after that, the missing data will be all imputed. Okay, so this is a crucial part, is for us to specify the design for cross-sectional analysis. So as what I mentioned, that for cross-sectional analysis, we will use the cross-sectional weights, right? So this is GSW5. This is basically the ad hoc wave 5 data file. So this is a cross-sectional weights for wave 5. So first I can subset my data to those that have a positive values for GSW5. So I'm saving all the respondents with the positive values with these weights. And then I can specify the design features. For that, I can use the SVY design variable to specify what is my ID variable. The ID means the cluster ID variable. So you can see that why this is the cluster 2. So for this, then the R knows, oh, I needed to account for clustering, the cluster in my estimation. Then you can specify the strata. So here I created this strata 4 strata variable called strata 4. So I can call that out. Then I can say, okay, the weights that I want to use is a GSW5 weight, which is a cross-sectional weight. And this is the data that I subset that only has that has all the respondents at wave 5. And then I can just do estimations and errors and design effects with this specified design. So later, you don't need to repeatedly tell R what is my strata, what is my clustering. You can only call out of, say design equals DES, which is defined here. So you've already specified what a DES means. So you can just tell R, this is my design, and I'm interested to compute the mean for body weight, the imputed body weight variable. And I'm interested to get the design effect for this as well. I can also do that for the binary proportions. So whether they got medical care in the past 12 months, dental care in the past 12 months, also like just tell R what is your design. So you will notice that all the functions here has like SVY at the front. So these are special functions from the survey package that is designed to make a survey estimation. So after that, I just wanted to make my results prettier. So I just, saved their outputs into different variables, and then I consolidated them into a data set called the result, and I outputted it here. So you can see this is my variable, this is their type, and this is their estimate, this is their design, their standard error. And this is their design fact. So you can get the design factor just from, these estimates because you already said that. So the design fact, you can see that it's not trivial, right? When if you are just doing a simple random sampling with equal weighting, without a stratification clustering, then your design factor should be 1. But because of this complex design and weighting adjustment, actually in animal health, you can see the design factor is about 2 or 2.5. And that varies for different variables. So the design effect is different. And if I'm just wanting to know the design effect due to unequal weighting, I can use the Kisch's design factor function, DEFFK. And that can automatically compute the unequal weighting effects for you. So that's 1.6. That's purely variation due to the weighting, not considering stratification or clustering. Okay, so I saved my imputed files into this file, and which I've also shared with you. And with that, I also can do a survey weighted logistic regression. So in order to do that, I can use this function called SBY-GLM. So for example, here I'm interested to see how medical care, body weight, sex, race are associated with dental care dependent variable. Similarly, I needed to tell R, this is my special survey design, so it can account for it. And I wanted to do a logistic regression, so I use this special function here. And then I can summarize my model results, and then R will tell me, okay, so this is my coefficient, standard error, t-value, p-value, so which are like typical, right? You can also compute like odds ratios based on the model results. So you can use the summary, the model fit object, use the functions to get the odds ratios. So the odds ratios will provide you, this will show you the odds ratio, and there are confidence intervals for different variables as well. So those are the same. So the key concept here is that when you are analyzing survey data, right, you need to use the special SVY functions in R, and then specify your design features in order to do proper estimation for longitudinal studies. So these are cross-sectional. And the second part gets into longitudinal. So just for demonstration purpose, I kind of generated the medical care variable for you for wave 1, 3, 5. Okay, so I have variables from 1, 3, 5. And then I output that data into what I call ad health imputed wide. So you can see the data file here. So you can see that I added more variables. So let me make it. So you can see that I made 3 new variables based on this variable. So this is, this is what I call the wide format of the longitudinal data, right? So you have the repeated measures as different variables at different times. And then one way we can do for longitudinal studies to study changes is that we can do pairwise comparisons across waves 1, 3, and 5. In order to do longitudinal studies, first, as what we did before, is that we should subset longitudinal samples to, to cases with positive longitudinal weights. Here, this is a case that I don't know how to construct longitudinal weights 1, 3, 5. but I have longitudinal weights 1, 2, 3, 4, 5. So that's good for analyzing those specified waves as well, because cases with those weights, they responded in waves 1, 3, 5. So you can subset to them first, and then you can specify your design that way as well. Like, what is your clustering variable? What is your stratification variable? What is the weight variable? What is your data set? And because we're analyzing longitudinal study, we should create paired differences. For example, if we wanted to compare wave 5 with wave 1, then we needed to compute their differences. Sorry. Okay, so we needed to compute a variable which is comparing the differences between the wave 5 medical care status minus wave 1 medical care status. Because we are not, for longitudinal study, this is repeated measures. So we can do the paired analysis. We can't just do like treated wave 5 and wave 1 as two independent sample and do t-test that way, right? So we needed to compute the differences at the person level. And then we could compute their survey mean for each differences and see, how much different, and we can also check to see their confidence intervals. So here I'm just getting their survey means and also computing the confidence intervals. So you can see that, if I'm comparing wave 5 and wave 1, this is the proportion of the difference, which is the estimate, and that's the standard error. And then we can compute the confidence intervals and getting the p-values. So that's how I can do like a simple pairwise comparisons across different longitudinal studies. But if I wanted to do like model-based longitudinal comparisons across different waves, then I needed to use like SVY, GLM, like doing a generalized linear models. That requires an additional step that I needed to reshape the wide variables to the wide data set into a long data set. So it will be one row per person per wave in order to do this type of analysis. So you can see how I'm doing it. I want to share all this code with you. So if you are doing your analysis, you can use my code as a reference. So let me show you how that long looks like. So the long looks like this. So basically, you can see that for the same, ID, I have, there, I think one thing might be omitted here. So you can see, they have wave 1, status, wave 3 status, wave 4, wave 5 status, and all of that. So you are actually converting this data into a long version, and to do that, you need to create another variable to indicate the time for the long version. And then you needed to specify, so these are just the, the long version. And then you need to specify your design that way. So your ID will be, there are two clustering IDs. One is the clusters in your sample design. Another AID is because you are having the repeated measures for these particular observations. So that's another layer of clustering you need to consider your longitudinal analysis. And then you specify the strata, weight, and then you can use the SVY GLM. Here I'm just doing a very simple comparison. So I'm looking at whether wave has a significant effect on the medical care long variable, and then summarize it. And you can see, okay, wave 3 and 5 also both have significant effects on the medical care, your dependent variable. What I didn't show you here is that you can also add other covariates into this comparison as a control covariates in the model analysis, right? So that gives us more flexibility to use regression analysis to do those longitudinal comparisons. You can also looking at interaction effects between wave and, for example, dental care and all of that. So you can build fancy longitudinal models using something like this to study, like, the developmental trajectory patterns or other kind of longitudinal changes as well. So here I just compute the comparisons and odds ratios based on the model results. So here are just the examples about how we can do model estimations. All right, do I get any questions here?
I've been trying to fend off questions in the
Okay.
chat so that you could finish.
Thank you so
Well,
much.
Yeah, it's okay. But yeah, there's definitely some good questions people are raising. So I'm responding to a couple of them, but maybe you can respond to Leon's here. So she says, what if a respondent is missing for some waves? That is, not every respondent has data for every wave. Could we still construct a longitudinal weight?
Yes. So that's covered here. It is because if you think about it, you have a so this is when, like, you have another layer of non-response in your data set. So you have, they responded at this wave, but they didn't respond in another wave, right? So only a subset of them responded in another wave. So you can model, like, what's the likelihood for a case to be responded in both waves or these multiple waves. So you can do an additional non-response adjustment and then do a calibration to create the longitudinal weights for that purpose. Does that answer your question?
Yep.
Mhm.
It
Yeah,
really, it's an issue of whether you want to look at individual change, right? This is assuming
Yes.
that you need data at each time point where you want to look at, for a given person, how they're changing from one point to the next. If you just want like marginal estimation at each time point, that's a little bit different story. What Dan's outlining is here, you really are interested in the change for a given person over time. That's the primary focus here, so.
Mhm. Yeah, and multi-level modeling, I think we could have another workshop for that.
Yeah, that's what I was trying to say. It's just it's complicated. There are good references out there, but definitely complicated. Yeah.
Yeah, so so just the conclusion is we needed to have the weights and then we need to know how to apply it. And there are a lot of other advanced topics, like how we can construct weights for time to dependent confounding effects. Refreshment sample is also a thing for longitudinal studies. So I have put some papers here. So if you are interested, you can read those papers.
Okay. Well, thanks, Dan. I think we have to give you a nice virtual round of applause. This was a very well constructed workshop, and love the examples, the materials, everything was fantastic. So, and again, your presentation was very clear, very easy to follow. So, I'm sure a lot of people are going to benefit from this recording. So, really, thank you for doing this. It was quite good. And like Dan said, there are plenty of references out there, but I think like the code that she's provided as part of this workshop should give everyone a really good starting point for making sense of longitudinal data and understanding how to use weights correctly. So really, thank you. This was very good. So does anybody have any final questions or comments before we ultimately sign off here? Or any questions or comments? Okay, not seeing any. Well, thank you again. Thank you again to Dan. Feel free to reach out to the various NIMLAS email addresses if you have questions. following this particular workshop. Again, don't hesitate to download the materials right now so that you have them in your possession while we try to make sure they can stay up there on the website. But yeah, download this stuff while you can right now. And again, we really appreciate everybody's time today and being here for this workshop. So thank you very much, and stay tuned for upcoming NIMLAS events. And thanks again to Dan. So, yep. Okay, thanks everybody.
Thanks. Bye-bye.
Bye.